Okay, so welcome to this morning session on the geometry and representation theory of geometry. Our first speaker is Shrawan Kumar. We'll talk about the representation supported by the orbit closure of the Determinant.
Thank you very much, and thanks to the organizers for the invitation. I do not have really very new results. So you may have, some of you may have heard this. These are some variant of this talk, but I do see at least some new faces. So maybe it will not be a totally futile exercise. So let me begin with some notation. So let's see. How do I erase? That's here. I have to go here. Okay. So let V be a vector space of dimension m, and this is a vector space. Everything is going to be over complex numbers. So let's start with a vector space of dimension m, and let E be endomorphism of V, which is also same as V star. So this, of course, so dimension E is m squared. And now we have a function from E to C, which is the determinant function. So if I take a m by m matrix, I can take its determinant. And determinant, of course, is a polynomial of degree m. So it's a polynomial of degree m. So I can think of determinant as an element in Sm of E star. So I just think of this as an element in the ML symmetric power of the dual of E. And thought of this, I'm just going to write this as, I'm just thinking of determinant as an element here, and thought of this as an element here, I will just write it with a capital Det. Now, GLE acts on, of course, E as the standard representation, and hence on E star, and hence on the symmetric power. So GLE acts on let's call this something. So let's call this Q. So acts on E and hence on Q. So I can take the GLE orbit closure of this determinant function. So this is a subspace of Q. Subspace, not like the vector subspace, some variety of Q, and I can take its closure. So this is going to be one object, which I will just call it X det. So that's one object. The other object is so let's fix two things. Let's fix n less than m, and also fix a basis of V, and let's call it EI. So that's this basis E1 through E1V. So then I can define this padded permanent function. And I'm going to call it P Mn. So this depends upon this pair Mn. So Pmn is nothing but, okay. So since I have fixed a basis of V, then I can write any element E as a m by m matrix. So let's write this, okay. So this is going to be a matrix n by n size. Actually, no, sorry. It doesn't matter, but let's follow what I have So let's just write x11 here, and in this bottom right corner I will put this n by n matrix. Okay, so this is a m by m matrix. So okay, H. So let's call it an. So this is going to be okay. So this is not determinant. This is x1 1 to the power m minus n times permanent of an. So this is the bad way to write this. Where a is now this is, I'm calling an. Oops. Maybe I should not write 2 below. Okay, so this is again, now for a m by m matrix, I am taking this entry, the first entry, raising it to power m minus n, and then multiplying that by permanent of this bottom right n by n block.
So you have 4 x11s in this diagonal and 0 out. That's what you mean? Or
Sorry.
in this description of the matrix A, you have x11 occurs along this main diagonal?
No, there's just one.
No. Yeah. This is just a number.
No. He's taking permanent of A in where A is bottom, so it's all right.
A is just the generic.
This is generic.
Generic.
He's not using all his coordinates. He's just.
Yes, okay. So A is a m by m matrix. I just write it as xij.
I was confused.
Okay. Maybe it's not your fault. Maybe it's my fault.
Way of introducing notation, I understand.
Okay. So now again, this becomes a polynomial of degree m. Okay, because this is a polynomial of degree n, and now I have blasted it or padded it by m minus n degree. So it's a polynomial of degree m. So again, I can think of this as an element. So again, I'm going to think of Pmn as an element in Sm of E star. And again, I can take the GLE orbit of this Pmn, and I can take its closure, and I'm just going to call it xp. And I should really say mn. Okay. So now these are two closed subvarieties of Q. So they are both, so x det and xp mn are both closed cones in Q. So they are both closed cones, means they are invariant or stable under C star usual homotheity action. So in particular, so this implies that if I take the affine coordinate ring and this, so this is the affine coordinate ring, are modules for the group GLE, which I'm just going to call it as G. So these are modules. Now let's, so I'm going to define two numbers. So I think I'm just going to not bend myself too much. So there is also MNE, which is all the n by n matrices of n by n type. So MNE also acts on this det. Mind that usually the action is by G inversed. So usually the action, so G on any function f on a element x is f of g inverse x. But I'm just going to change it into a right action. So M and E will act on the right. So, but that's not going to change the orbit structure. So I'm not going to worry about that. So I'll just say that this is the right action. So I'm just going to denote that. So that's also sitting in Q. So now let's define two numbers, fix n, and let Mn and M bar n be the smallest integers, so that this so I will just consider this orbit GLE of this permanent is sitting inside this one, M and E. So that, okay, right, so and similarly, let's take M bar n, the smallest, yeah, so that this x for Mn is sitting inside x. So now Valiant, and this is 1979, made a conjecture that this function Mn, conjecture, Mn is not dominated by any polynomial in N. And so this is some algebraic version of Cook's famous P not equal to NP conjecture. Right. Okay. So, I mean, even though I do not understand, but since there are many computer scientists here, so maybe I'll just say this as the statement that this perm does not belong to this class VP. That's what this means. Now, clearly, M bar n is less than equal to Mn. So M bar n is less than equal to Mn clearly because the orbit Mne, of course, GLE is dense in Mne, so in particular the GLE orbit closure will contain at least Mne. So M bar n is less than equal to Mn. And now Mulmule and Sohoni, in a series of papers, more than half a dozen papers, they made conjecture not in half dozen papers, but they made this conjecture that even this function M bar n is not dominated by any polynomial. And of course, since M bar n is less than equal to Mn, of course, if you prove this conjecture, then you would have Valiant's conjecture immediately. And again, for the computer scientists, this means that perm n n bigger than equal to 1 does not belong to this class VPWS bar. But nobody will ask me what it means. So, okay. Right. So not only they means Mulmule and Sohoni made this conjecture that m bar n is not dominated by any polynomial function, but they also laid out a program as to how to prove it. Now the advantage, at least for people like me who dabble into algebraic geometry and representation theory, is that this object is more readily can be used in algebraic geometry and representation theory, and that's where I'm coming to. Okay. So maybe I should at least keep this notation V dimension M. E is endomorphism V and Q is SME star. So I'll keep this notation. Okay. So now, so as I said, I mean, not Maliketan Mulmule and Sohoni made this conjecture, but they laid out a program, and this program is as follows. So the question is, when does X, this perm Mn, sits inside X dat? So let's start. Let's find the first M, the smallest M, where it stops to be there. So, okay, so I have to say something. So for large M, if you fix an N, for large N, it's a old result that indeed this variety is sitting inside this for a large M compared to N. And this is roughly of the order of 2 to the power N or 2 to the power N plus 1, something like that. So this is this variety is contained in here for large M. So now you want to look for the smallest M where it ceases to be not contained in there. So let's say that it's contained in there. So the affine coordinate ring of this will surject onto the affine coordinate ring of this one. I mean, it's a subvariety if it is contained. So if this is contained, then because it's a closed subvariety, both are affine. So then at the affine coordinate ring level, this map will be surjective. And of course, this is a embedding, G embedding. So it's a G equivariant embedding. So this will be a G module map. So in particular, if this is surjective, so in particular, if I take any representation of G, so keep in mind that G is GLE. So if I take any representation G, V lambda, where lambda is a partition, into at most M squared parts, because we are taking G of GLE and E is M squared dimensional. So V lambda, so lambda is a partition into at most M squared parts. So in particular, multiplicity, so multiplicity of V lambda in C of X per Mn will be less than equal to multiplicity of V lambda in this side. So in fact, Mulmule and Sohoni not only conjectured that M bar n is not a polynomial or not dominated by a polynomial, but they also said that, okay, so this is another conjecture due to Mulmule and Sohoni. And this conjecture says that if, no, right, so X perm, so let's write it precisely. So for any M bigger than N, X perm Mn sits inside X det if and only if there exists one V lambda or some V lambda such that this multiplicity is strictly bigger than this multiplicity. So one side I have already shown you, it's trivial, but they conjectured that it's the other side. Now, depending upon the day and the sunlight, I believe or not believe in this conjecture. Today it's cloudy, so I don't know. I'm a little bit more gloomy today.
I think the conjecture was slightly less strong than you stated.
Okay.
Because it just conjectures that it's not for every M and N, it's just that there exists sequences, perhaps very sparse subsequences.
Okay, is that...
It's all right, but today, as you said, cloudy, so
Okay, so I stand corrected. So in any case, I mean, there is some yeah.
in the clouds today.
Yeah, right, exactly. Okay, so, right. So, at the very least, I would say that this seems rather hard. And this is a rather hard problem, of course, as you all know. Right. So let me give you two, and which probably should be called as somewhat negative results. So what one is looking for? So one is looking for a representation V lambda, which occurs on the permanent side, but it does not occur on the determinant side, right? So suppose I were to prove that every representation occurs in the determinant side. Suppose, hypothetically, suppose I were to prove that every representation occurs on the determinant side, then forget it, right? Then you can't have this approach. Of course, I mean, you could refine it that the multiplicity should be bigger, but this Mulmule and Sohni conjecture that not only the multiplicity, but even the occurrence gets problematic. Right. So I will just say that many times there are two different varieties which have the same affine coordinate ring, not as a ring, but as a G module. And in fact, there is a result by Briand and Alexeyev, which says that let's take a G variety, affine G variety, and let's take its affine coordinate ring, which is a G module. And now let's look for all affine G varieties which have the same affine coordinate ring just as a G module, not as a ring structure. Of course, the ring structure will completely determine the variety, but just as a G module. So this family of such affine varieties form itself a scheme. So there is a moduli, and this has been studied actually in some series of papers by Briand and Alexeyev, and also it's being followed up by some other Italians. So this is definitely the representations occurring in a affine coordinate ring does not determine the variety. So that's definitely, and there are very simple examples in repetition theory where this phenomenon occurs.
What did Alexeyev and Briand study?
Right. So exactly what I said.
Okay, could you repeat what you said?
Okay, so now you ask me the correct question then. So let's take a G variety, affine G variety X, okay? And let's look for a affine coordinate ring. It's the G module.
Yeah.
Now, I fixed X.
Yes.
Now I look for all possible affine varieties Y, such that the affine, G variety Y,
Yes.
such that the affine coordinate ring, not as a ring, but as a G module, is isomorphic
Yes.
together with the multiplicity.
Yes.
Such Y form itself a scheme. So there is a moduli. So I'm fixing the
Positive dimensional. So it's a positive dimensional set.
It could be zero dimensional sometimes, and it could be positive dimensional sometimes.
That was my question.
Right. Okay. Right. So many times it's positive dimensional, but sometimes it could be rigid, and it could be zero dimensional. But there has been a fair amount of study about this moduli. So the point I am making.
The complexity is very different from.
I just want to say that the module structure does not determine the variety. That's what that's all I'm saying. Okay, so now one very traditional way in representation theory, at least, you study C of any G variety X. Typically, what you do, that X is normal. Then you take and suppose X is G orbit closure. So suppose X is some G orbit closure, a single G orbit closure. So the way you study the affine coordinate ring of X typically is you study the affine coordinate ring of GV, which is generally a very simple object because it's nothing but you take ring of functions on G and you take H invariant where H is the stabilizer of V. And a affine coordinate ring of G, of course, is given by the Peter-Weyl theorem as a G module. So in principle, that's a very easy problem. But the hard part is these are functions only defined on the open orbit, how to extend them. And this extension problem is generally difficult. But if you have a normal variety and you have some control on the divisors at infinity, then you may have control. And there are many representation theoretic situations where that's exactly what happens. That you have a normal variety and you have some control on the complement of this open orbit, and you can use that quite powerfully to study. So first negative result. So theorem, and that both of X det and X perm Mn are not normal. And in fact, not only they are not normal, but I suspect that the non-normal locus is really very large. So it's not that it fails in a moderate way. Actually, it fails terribly, but that's not something I have proved. That's my hunch, that this will be not normal. Okay. So the next result.
I don't understand when something's not normal, how I thought the non-normal locus has a minimum codimension.
Non-normal locus is a subvariety.
Yes.
Correct? Now you can ask this subvariety is 0-dimensional, 1-dimensional, or 1 billion dimensional. Correct? Right. So I'm saying that my hunch is that it will be 1 billion dimensional, not 0-dimensional or 1-dimensional.
But can you describe it in terms of the codimension?
That's what I'm saying. So, so codimension could be, actually my hunch is that the codimension is actually 2. No, sorry, 1. Sorry, codimension is 1. Exactly. Yes. Right. Okay. So now I should say that only general positive result is due to Landsberg and Manuel and Resayer, and that is, let's get that straight, n squared plus y. So, yes. So what? And all three of them are here. So they proved that this Mn is at least m bar n is at least n squared plus 1. Is that correct? Am I getting it right?
Greater than or equal to n squared over 2.
Oh, n squared over 2. Sorry. Is that? Okay. So that's the. So at least m bar n is quadratic in n. So that's the positive result. Now, okay, so as I said, let's try to follow this program. So we are looking for representation which occur on the permanent side, which does not occur on the determinant side. right? So now first of all, let me make one simple lemma that any v lambda which occurs in this x perm, C x perm Mn has the property that, so this lambda is a partition, lambda 1 at most lambda m squared parts, but any v lambda which occurs in here has the property that, let's break it here, lambda n squared plus 1. So let's break there. So everything has the property that lambda I is 0 for all I bigger than n squared plus 1. That's a fairly simple result. I mean, it does require a proof, but it's not terribly difficult. That anything which will occur on the permanent side will have this property. Now, okay. Also, there is another simple result, which let me mention, that any v lambda which occurs in either of those, in Cx det or Cx perm Mn, satisfies the total length of, no, what is it called? Is multiple of, so what is it called? I mean, so this is number, yeah, so it's summation lambda. I forget what it's called something. So that's multiple of m. Okay. So now, I come to another theorem, and this says
sorry, what did you write on the read it? Which occurs in Cx det? Is that, what's that?
Right. I did a very bad job in Cx det or Cx perm Mn. Either of those two varieties satisfy this property. So now the next theorem is that, so take any lambda such that lambda is of the form lambda 1, lambda 2, lambda m, and then zeros. This is lambda. Take any lambda such that lambda is of this form, then the m lambda occurs in Cx det. Now let's compare these. Oops, sorry. So let's compare all these lemmas and results. So first of all, any v lambda which occurs in this side must die out beyond n squared plus 1. Okay. So if n squared plus 1 is, let's say, less than m. Less than equal to m. So let's take n squared plus 1 is less than equal to m. And we can always assume that, because there is already, by result of Landsberg, Manuel, and Resayer, there is a quadratic bound which is already known. So you are trying to improve the bound and eventually show that, in fact, there is no bound, right? So we can always assume that at least m bar n is quadratic. So I'm saying that let's take any m which is bigger than equal to n squared plus 1. So any representation which will occur here will taper off beyond m. which will be 0 beyond m. So it will satisfy this condition.
And can you control the multiplicity?
Second?
Can you control the multiplicity of V and lambda and degree d product?
I didn't follow.
You control the multiplicity.
Multiplicity, no. Multiplicity is a mess, I tell you. I mean, multiplicity is, no. No, that's I would not go there. No, it's a mess. So, yes, so let's come back. So if m is bigger than or equal to n squared plus 1, so this sequence dies off beyond lambda m, even before. And this theorem says that if you go up to lambda m, then Vm lambda occurs in that. And let's combine that any lambda which occurs in either of those must satisfy that this total size of lambda is a multiple of m. Now, these two do not say that Sohoni-Mulmole conjecture is false, but it does say, okay, but there is provided. No, but and there is a very, very strong evidence that Allen-Tarski conjecture is going to be true. So now I'm going to talk about Allen-Tarski. But before I say that, what I was just saying, that, any m lambda will occur here. So this is basically no constraint if I'm taking m to be more than quadratic. But this is, and any such lambda which will appear here is of the size multiple of m. And I'm saying that if you saturate this by m, then this will occur in here. Provided, of course, this Allen-Tarski conjecture is true. So it does say that to find such a lambda, so we need to find some lambda which occurs on the permanent side, but does not occur on the determinant side. I'm saying that this problem becomes very difficult because now you have to worry about, general techniques in precision theory are not too bad when you go to saturation. When you go to saturation, then repetition theory is more controllable. So, but if you go to saturation, there is no hope. That's what I'm trying to say. Right? Okay, so now.
What this says is the saturated semigroup is
exactly. No, if you saturate.
So you can't look for.
Exactly. See, because with saturation, there are these Horn inequalities. You can deal with lots of things. You have some control or a good control. So this theorem says, forget about saturation. I mean, you have to really look for needle in a hay. I mean.
Hay in hay is hard too.
Say that again?
We discovered yesterday that looking for hay in a haystack is hard too.
Not finding the hay in the haystack.
Okay. Right. So these are the results. Now, I've not told you anything about proofs. I mean, some proofs are a little bit longer than the others. So they use a couple of things, but basically a repetition theory of GLN and symmetric group and Walsh-Schur duality and things like that. So not too sophisticated techniques. It does not use any perverse sheaves or anything like that. So it does not use. Say it again?
Things that I don't understand.
Okay, so.
Elaborate a bit on the connection with the Allen-Tarski?
Yes, sorry, say it again?
Can you elaborate on the connection with the Allen-Tarski?
That's what I'm going to tell you at least what is Allen-Tarski.
That I know.
Oh, that you know. Then you can just sleep off now. I'm sorry.
We're both good friends, so.
Okay, I see. Well.
It's not too hard to explain.
Right, but it will take. But let me first at least. Is there anyone here who does not know what is Allen-Tarski? If everybody knows, then I have to explain. Okay. Okay. So this is Allen-Tarski, and that's by 1989, something like that. Okay. No, 1992. So this is about these magic squares.
Latin squares.
Yeah, Latin squares. I mean, isn't it also called magic squares?
No, that's Emmanuel Briand's thing. That's a different thing.
Oh, is that right? Somehow I. Okay, Latin squares. Of size M. So what is a Latin square of size M? So it's a M by M matrix, M by M box, where each row is a permutation of, so each row and each column is a permutation of 1 through n, 1 through m. So each row is a permutation of 1 through m, each column is a permutation of 1 through m. So let's say if I take m equals 2, then we have 1, 2, 2, 1. And then we have 2, 1, 1, 2. Only 2. Right. Now, so to any such, so this is called Latin square. Okay. So I am fixing an M, and let's consider the set of all the Latin squares. Now, to every Latin square, you associate a sign, +1 or -1. So sign of a Latin square. So as I said, every row is a permutation of 1 through m, and every column is a permutation of 1 through m. So let's just call it permutation sigma 1, sigma 2. So these are columns, sigma m. And I'll just call S1, S2, Sm. Those are the permutations of the rows. So sine of a Latin square is nothing but sine of sigma I from 1 to m, product of sine of Si from 1 to m. So you just multiply all the signs of rows and columns. That's called a sine of a Latin square. Now there is also called a column sign. And I'm sure you can guess what it is. And that is exactly, by definition, just sine of columns. So sigma I from 1 to m. So that's the column sign. And similarly, of course, you can define the row sign of a Latin square. Now, Alan Tarsi made this following conjecture. And that is that conjecture, and this is Alan Tarsi, 92, that take m even, then number of even Latin squares of size m is different from number of odd. And even just means that the sign is +1, odd is sign -1. So they made this conjecture in 1992. And then there was a result due to Huang and Rota. It said that Alan Tarsi conjecture is equivalent to saying that the column sign, number of column odd Latin squares of size m is different from number of column even Latin squares. Of size m. Okay, so whether we take just the column sign or the total sign, it doesn't matter so far Alan Tarsi conjecture is concerned. Now, there was 2 papers, Driscoll and Glynn, and so there were 2 papers, Driscoll that is 97. Proved that L&RC, I'll just cite AT conjecture, is true for M equals P plus 1, where P is a prime. P is odd prime. And then Glynn, and that is, 2010 actually. Oh, I didn't realize that it was as late. It's true for M equals P plus 1.
Minus. One of them is minus.
Oh, sorry, yes. Exactly, of course. Right. Yes. Otherwise, it will be scandalous that after 13 years. Okay.
What is the situation where for M odd your theorem is always true or is not true?
The two are equal trivially. Just take transpose. They come in pairs, positive and negative, or even a negative.
No, the question is not about the conjecture Alan Tarski, but about your theorem. But each time we have one M where the conjecture is...
Same for M, same M. That's right, same M, exactly.
And in particular for M...
Even. No, okay. I am only going to consider M even for some reason. I'm only going to consider M even. And for M even, yes, right, good point. So take here. So actually, I don't have to say that theorem. Then occurs in, provided L&RC conjecture is true for that M, for that even M. So, same M. Exactly. Now, okay. If I'm allowed to give an exercise, prove that for M odd, these numbers of odd is same as number of even.
So you might as well assume M is prime plus 1.
There you go. Exactly. That's right. Exactly. That's exactly right. That's exactly the point. But you see, for a mathematician, I mean.
So what I'm saying is, so can I say one thing?
Oh, you can say more than one thing. But if you don't mind, can you say it in a few minutes? Okay. So now, this is a conjecture, of course, in like combinatorics. Now, there are some beautiful analogs in representation theory which I want to mention. Equivalent formulation of L&RC, actually more like this, the L&RC column. I will just say column L&RC for M even. And I still think it's quite appealing. And I and Joseph have spent many sleepless nights, and we have come up with many wrong proofs over a period of time. And this says the following. So this is the same M. So let's take SM of CM. Actually, which was V for me. So I just, not E, but let's take V, and let's take the mth symmetric power here. Okay, so I take the mth symmetric power of V. And keep in mind that V dimension of V is M. Now, let's choose a basis, which actually already I chose at some point, and I called it even EM. V. And now in SMV, of course, we have this element, I mean, the most canonical element, okay, one can debate that. But at least there is a very canonical element, E1 times E2 times EM. Right? So that's an element here, and I just raise it to power M. That's what I do. I just raise that element to the power M, so that becomes a element here, and let's just call it V0. So I've given you a very specific element in this SM of V, and GLV of course acts on this. So let's take the GLV module generated by this. So this is the GLV module generated by VG. Okay. So GLV module generated by this specific vector. Now, so there is a simple result.
The highest weight vector. It is an highest weight vector.
No.
So this is not a
Nicholas, if it were highest weight vector, I don't think that we will spend sleepless nights on this. Unless we are too stupid, which could be a possibility. I mean, I don't rule that out. I definitely do not rule that possibility for me, not for Joseph. I can definitely do not rule that possibility for me. Okay. So now it's a well-known, not too hard a result, that SM of V contains a unique copy of SLV trivial module. That's a simple result, that SM of V contains a unique copy of SLV trivial module. So now equivalent formulation. So equivalent formulation of column L&RC is that this module GLV V0 contains this unique copy of trivial SLV module. Okay, it's so appealing, and I mean, as a repetition theorist, I mean, you feel like, oh my God, you should be able to prove it in 2 hours, right? It should not take more than 2 hours. But here it is. I have already said that I and Joseph have spent many sleepless nights on that, but that does not mean, I mean, we don't have the right idea. So I really encourage you and all.
Can I understand this last?
Yes.
Lemma is contains unique cell.
That's a lemma, without any qualification, that SM of SMV contains a unique copy of SLV trivial module.
Is that something related to constant thing?
I don't know. I wouldn't bring constant there.
It's more elementary.
Yeah, no. I mean,
Then after that, what you say?
Just even tensor power contains unique copy, right?
but
Even tensor power, SMB, tensor SMB contains
from, I am not sure about that. I don't remember offhand. Yeah, I probably you are right. Probably you are right. Okay, so equivalent formulation says, so L&RC conjecture you understand now? Right. So it says that L&RC is equivalent to saying that the GLV module generated by this specific vector which I wrote down contains this unique copy of SLV module, trivial SLV module. So this is a G module. You decompose, and it does contain the trivial module in it. That's what this, and it's an equivalent formulation. Okay. Actually, my time is more than up. There is one other equivalent formulation which I and Joseph have arrived at, and hopefully it will see light of it sometime. And it will take 1 minute to describe that. Another equivalent formulation. I should really stop, but another equivalent formulation is that you take this function over SUM. Okay, you take this SUM, this compact group SUM, and you take the matrix entries Gij, and you take the product. Okay, take the product of the matrix entries of this matrix, and you take the Haar measure on SUN, and this is non-zero. So this is an equivalent formulation. This was arrived at with Joseph. And so there are some other equivalent formulations, but I better stop. In fact, I'm already well over my time.
Other comments or questions?
So there's a lot of literature on the combinatorial literature on the long task. I don't know if you follow that one. Let me mention just one. There is a beautiful conjecture of Rota, so just the
Yes.
personalities make the whole thing suspicious, which is really fantastic. So I think...
No, 1 minute. So there is an equivalent formulation by Rota.
No, not this one. No, Rota had many things. It's a different... Rota is a conjecture, which says the following. You have a finite dimensional vector space.
Okay.
And I give you, so it's n-dimensional, and I give you n bases.
Correct.
This conjecture says you can rearrange these vectors, pick one vector from each base,
I
and
know
make
that.
the basis, pick another one. And if I remember correctly, this is, first of all, it's very closely related to one
Right, exactly.
Perhaps they're equivalent.
It is equivalent, and just to, if,
Let me say one more thing. There is-
no, but before you say one more thing, let me correct you that this is not just Rota, it's Huang and Rota.
No, this is different. This is the colorful conjecture, not the column lines. It's a different conjecture. Shrawan.
And so there is work by Shmuel on. There is stuff that I keep seeing. If you want, I can dig up for you more references.
Oh, I definitely would love to.
Work by Shmuel on. You saw the
Yeah.
Shmuel on paper, which connects along Tarsi with Rota's conjecture. There is more recent stuff on this, so that would be extremely interesting.
Also, there is a more recent work by.
More recent stuff. I forget the guy's name, but.
But is there a proof more general than P minus 1 and P plus 1?
Say again?
Is there a proof of ln Tarsi beyond P minus 1 and P
No,
plus?
I'm not talking about this. No. There are particular values. Perhaps there are more cases where the conjecture is known to be true. That's one line of research. But I'm talking now about something else, which puts the Alon-Tarsi conjecture in other contexts. So, for example, if I remember correctly, it's certainly very closely related to this Rota basis conjecture.
Right.
And if I remember correctly, perhaps even the two are equivalent.
They're equivalent.
No,
I don't say
they're not.
Oh, okay.
In this own article that
So you
well,
probably read the Shmuel
Yeah.
later than I did. So what does Shmuel prove?
I don't remember, but he definitely does not say that they're equivalent.
So Alon-Tarsi implies Rota, perhaps.
There is one
At least an
implication. There's an implication that goes.
But there is
both
more
ways.
recent work on this. I'll dig it up. There is a guy, I forget, he spoke in our seminar a year ago, and I'll find
And he's a combinatorial theorist, computer scientist?
He was talking about this on our
There's a lot of activity.
Oh, I would.
Around that, and it would really be interesting to understand. So another small
I don't
comment, which I don't know if this is at all relevant.
Yes.
But there's another way of looking at the Latin square, which, for me they're related, but I can't say.
Okay.
That, so a Latin square, as you described, is just an n by n array, the numbers of 1 to n, appear once in every row in every column. Equivalently, it's an n by n, a three-dimensional array, n by n by n, of zeros and ones.
So it's a cube now.
Exactly.
Yeah.
Every line contains exactly 1, 1, and the rest are zeros. Why? You take this, think of the matrix as you described.
No, 1 minute. So it's a cube, n by n cube, and
Let me back up a second. You can, a permutation matrix, you can describe as an n by n array of zeros and ones, where every line, row, or column contains exactly 1, 1, right? That's a permutation matrix. Now take this one dimension up. It's an array of n by n by n, where the entries are zeros and ones. You want to call it a three-dimensional tensor file, which that helps. And every line, so now there are rows, columns, and shafts, and each one of them contains exactly 1, 1. What's the connection is very simple. Think of the usual description that you gave as a topographical map, which tells you in what height above your head the one is sitting. And so, these are all objects that are,
I am.
intensely investigated electron combinatorialists, and I just wonder if there is more than, the superficial connection.
Uh-huh.
I think actually one of those two proofs uses.
Exactly, hypergeometric. So this is hypergeometric function. So this is what, if I understand it correctly, it's the hypergeometric function, and Glenn has used it very powerfully. Yeah.
We can try and dig up the literature.
And yes.
In your saturation results, you can replace m by the smallest prime, which is bigger than n. is surrounded by 2M.
So say it again now.
You can use the results by Driscoll or Glynn.
Yes.
You can replace M by the smallest prime bigger than M for the saturation.
Exactly. Of course.
You go at most to 2M.
Exactly. I mean, basically that's what Ketan said. No, I completely, but you know, as a mathematician, you want to, I mean, you know, you're not, I mean, actually, Ketan, you had some remarks, son.
That in complexity theory, this is a barrier result, okay, which is an evidence against a peak. Like in complexity theory, there are results like natural truth barrier, which says that the asymptotic techniques that they were using in complexity theory are not going to work in the context of P versus N. This is a similar thing which is saying that asymptotic results are not going to work.
That's precisely what I said.
Yeah.
Right.
So it is an analog of natural proof barrier in complexity.
I see.
So it is an important thing.
Correct.
But to a complexity theorist like me, this was expected. That
I see. Okay. I see.
So one shouldn't get depressed by such things. That's all.
Okay, good. That's good to know that there is still some light in the day. Yes.
I want to ask a
Yeah.
question because I don't understand why to exclude the multiples of M implies that there is no asymptotic obstruction. There are a very large lambda which are not multiple of M.
Yes, but then multiply them by M. And
This sentence was used several times this week, and I never understand it.
No. So maybe I don't fully understand.
The assertion is there is no counterexample, there is no interesting vanishing
Right.
for multiples of 3.
Correct.
There are very big integers that are not multiple of 3. And it's so the conclusion is there is no asymptotic obstruction, and I can't understand this last section.
No, I don't think anyone was asserting there's no asymptotic obstruction. Just he's saying
That there is no asymptotic. You can't go asymptotically. That's what I said. So
it's something that you take the cone of all of these
not so-
and you can't detect anything.
exactly. That's all I'm saying. But are you saying something different?
There's no linear symptomatic
Yeah.
obstruction. You could base on a symptomatic.
I mean, but it is hard when you have a semigroup with holes in it to detect what the holes are.
Exactly. That's the point. That's exactly the point I'm making. But Nicholas, if you are making something different, which I'm missing.
Sometimes oddness can imply vanishing. For example, of big. Okay,
what?
maybe later. I'm not so.
So you're thinking there may be an index going on, like something being odd versus even.
Yes,
Maybe.
we know that congruence modulo some submatrices imply
That does
as
occur.
consequences on
No, that is true. I do agree there.
for some congruence.
Right. Exactly. Absolutely. No, I completely agree. But keep in mind also, I mean, this lemma 2, which is not on the board anymore, that the size of lambda has to be multiple of m. So you have to be careful. So see, there are two constraints that any representation which occurs on the determinant side or on the permanent side, the size of lambda has to be multiple of m, same m. So I am not saying, by no means I'm saying it's impossible. I'm just saying that it makes it a bit hard to locate such representations. Okay? There was some other, yes.
You said that the representation theory of the affine coordinate string of a variety does not describe the variety. Right?
Definitely not.
Yes. So are there examples where these varieties are orbit closures, so two orbit closures?
Yes.
And are there
Yes.
and also examples where these are orbit closures of points that are actually defined by their stabilizer? So whether the stabilizer is
Yeah, right. I don't know that. But for your first question, I can give you very easy examples.
okay.
Right. And what you do, you take any semi-simple Lie group, take its Lie algebra G, and you take let's say a regular semi-simple element. Okay? So let's take a regular semi-simple element. Let's just call it S. Now you take the adjoint orbit of this. This is already closed because it's semi-simple. Okay. Now let's take a regular nilpotent element. Okay. So N, G, and let's take this orbit and close it up. Now, these are completely different animals, but their affine coordinate ring has exactly the same representations, not only the same representations occurring with the same multiplicity. So you see, it's not only the same representations of the same list, but they have exact same multiplicity. And this is very simple example. And you can cook up lots of such examples.
P, what kind of Lie algebra?
Any semi-simple Lie algebra. You take whichever is your favorite semi-simple Lie algebra.
It's even more general, right? I mean, for any...
Yes, exactly. So I took regular semi-simple. I could take any semi-simple. There will be corresponding nilpotent element such that the G orbit of S will have exactly the same affine coordinate ring in terms of representations as some other nilpotent element. Yes.
It's very, very interesting to have examples like this where actually the points are defined by the stabilizers.
Absolutely. Your remark is absolutely well taken, and it was well taken long back, but...
So let's continue this discussion. Thanks again.